All right, I think we're ready to do the last bit of gears. So this is going to be AGMA contact stress and factor of safety. So last time we did the AGMA bending stress equations and the factor of safety for that. This one should be much shorter because a lot of the stuff that we did last time will carry over into this one. In fact, we'll start on the same problem that we had from last time. So what we're talking about here, let me pull this picture up here. So last time we were doing more of this kind of, the one I've labeled bending failure here. You can kind of see the gear tooth is just about to break off of there. And you can kind of see where it started some sort of failure over here at the root, and now it's almost all the way across the tooth. That's the bending stress failure, the one that the Lewis equation models, and then the AGMA equations refine. And that's what we did last time. This is what we're talking about this time. So now this might be kind of I don't know if this is extreme or not, but this is a really large piece that is broken out of the surface of the tooth. So the tooth itself is still intact. It hadn't like broken off of there, but there's this cavity in it. And that's what we're talking about here. Some people call this pitting. This is a contact stress. In fact, there's an interesting thing here. You can kind of see across the top here, it's all in a line, and then there's this chunk missing below that, but there's this line across here. And that's pretty common with these pitting failures, is you'll have a line across the gear teeth. So what happens, let's look at our little model here, if we can see it. Let's zoom in. All right, so we're looking at the teeth as they contact. Let's look at the ones by the arrows here. So this tooth coming in contact with this one. I need something to point with. This tooth coming in contact with that one. So as they move past one another, as this tooth here moves past the one here, you can kind of see it changes directions. It goes in and then comes out. In, out. So since it's changing directions, that indicates that at some point there's zero relative velocity between these two teeth, the teeth on the blue gear and the teeth on the black gear. And so if there's zero velocity relative to between them, then there has been a point in time, it may be a very brief point in time, but a point in time where the lubrication, if there's oil or whatever around here, has also experienced that stop, that change of from one direction to another direction, so that peak where it's at zero relative velocity. And whenever lubrication is not moving around, that's when you get failures. And since that in these gear teeth is going to occur kind of in a contact line across the face of a tooth, so across the face here, there'll be some line where that change from one direction to the other direction occurs. That line ends up repeatedly getting that area of no lubricant support. And so what you end up with is a line of pits across here. Now this particular picture has a line, but then a big chunk broken out. So these teeth are undergoing some compression. The teeth are pushing on each other. Below the surface, there's getting this harder kind of work hardening type thing underneath the surface where there's these compressive stresses, and then combine that with this line where the fluid, the lubricant, breaks down, or at least it's not moving anymore, and you have metal on metal contact, and then you'll eject pieces of the gear tooth, and you end up with these pits. Sometimes they don't end up as this big chunk, but there'll be lots of little pits all the way across here. That's what we're looking at today. Is this would also, eventually this is going to be a failure, whether it ends up being a broken tooth type failure, or just the fact that now you've got all these little metal particles floating around in your gear train. That alone could be a failure. But you certainly don't want these pits across here on your gear tooth. So that's what we're looking at today, is a contact failure. We do have a equation that will look at that. Let me see if I can. Here we go. AGMA contact stress, so it's equation 1416. There are two versions of this one again. One, they're the same equation, but they use different variables. So there's a C versus a Z, and an I versus a Z over here. F and B are different. CF and ZR are different. Basically, all the ones that include a unit of measurement are labeled differently. They mean the same thing. They just label them differently because they might come from an equation, or they might come from they might have units built into them. The K's don't have units built into them, so it doesn't matter, you know, if you use one or the other. They're just a ratio. But these that have units embedded, you need to use the correct one so that you end up with the SI units or the US units, and you don't mix them together. So that's why they label them differently, but they're the exact same equation. And so it looks, you know, somewhat similar to the AGMA equation that we used before for the bending stress. In fact, you can see some of these same things. The WT, that's the exact same as it was before. That's the tangential force, so there's no difference there. K naught, or well, K zero. It's not a zero. It's a KO where it's overload. You've got the velocity factor. You've got this size factor that we didn't really know what to do with last time. We didn't have any indication to do anything there, so we left it at 1. You've got the Km value that is going to be the same as it was before. That's the one that takes a long time to calculate. There's a CF. This is new. That's a surface condition factor. I is similar to, what was the variable it was before? Was it Y? YN? Let me look. Oh, no. No, it was J. It was J in the previous one. So in here it's an I. And F is still face width. dP is the diameter of the pinion. So a lot of these are ones that we're going to reuse. That's why it's going to be shorter today. Oh, here we go. I is the geometry factor is what it's called. So it's similar to J from the last one. All right, let's plug some of this stuff into MathCAD and see how it's going to work for us. All right, let's, I don't remember what I think your book uses this as sigma.c is the variable it uses. I'll go ahead and write it in as let's write it in as a symbolic equation so it doesn't complain that we're missing some of these. Okay, we don't have that one. We'll have to get it. W. Now remember, I have to use a subscript T. In here I could use the superscript T. In fact, I guess I could right now. It'll be all right. But this is the sometimes in MathCAD I have to use a subscript T depending on where this is in the equation. Your book does use a superscript T to mean the tangential force. Let's see what is in there. K O, KV, and K S. And then we're going to multiply times Km over the diameter of the pinion. I think I used a capital P there. And the face width times CF over I. All right. So like I said, some of these are actually half or more of these. We already know more than half of these. Let's go ahead and, since CP is the very first thing, let's go ahead and get that one. That's an elastic coefficient, talking about the relative elasticities of the pinion material and the gear material. So it is possible that the pinion would be made of one material and the gear made of another material, or maybe different alloys of the same material. In general, the pinion is going to be a harder material than the gear. So there is a way to calculate this with an equation back in, I don't know, chapter 5 or 6, somewhere in there, where you could go in and calculate this based on the two different Poisson's ratios. But we also have a chart. Let's see if I have the chart in here. It looks something like, no, that's not it. If I don't have it, we'll get it out of the book. It's similar to these. There it is, right there. All right. So table 14.8, the elastic coefficient. Again, this one does have both sets of units in it, so you'll see a number on the top and then beneath it a number in parentheses. The one on top is the US customary units, and the number in the parentheses are the SI units. And what you do is, if you're using the table, then you go in and find your pinion material over here, and you have 6 to choose from. And you find your gear material over here, and you have the same 6 to choose from. And then it works like a matrix. You intersect those, and that's your number. Now this one is kind of a rounded off number. If you were to calculate steel on steel, it comes out to 2,894, something like that. I don't remember the exact number, but it's it's close to. I think I said it's 2,284, or somewhere around there, which is close to 2,300. So these are going to be slightly off from if you go and calculate the numbers exactly, but let's just say that we do have a steel pinion and a steel gear, and we'll take this 2,300. Now it has oddball units. Square root of PSI or square root of megapascals are the units here. So don't forget that it has some weird units in order for it to work out. So square root of PSI, and we have 2,300 of those. So we just plug that into MathCAD. 2,300 times the square root of PSI. Okay. We have WT. We'll just go ahead. Oh, this is where it won't let me. I don't think it'll let me do this. Yeah, it doesn't know. So that's not what I wanted to do. I think I ended up putting it in as this. And we have it in pounds. So 95 pounds, that was our tangential force. K overload, we should already have this one. We just set it to 1. This is when you have some kind of impact loading on the gear or the pinion. There's some kind of, maybe it's in an internal combustion engine. That's the example I use a lot, because there's obvious impact loads when the cylinders are moving up and down, and the explosions are happening. So this, we're going to say, is just it does not have those kind of smooth running, or at least it doesn't have heavy impact loads. So we're going to set the overload to 1. We already did the velocity, or dynamic factor is what it called, 1.299. Let's go look at that one where we did it before. Here it is. It's the one where you have a quality factor. Now this whole thing is the dynamic factor. Let me move that up here. We'll call just this QV as the quality factor. So QV is the quality factor. The whole thing, KV, is the dynamic factor. So there's this quality. I think it ranges from around 3 to 13. We put ours at 5. That's one of the lower quality gear constructions. There are 2 coefficients, A and B. Well, B isn't a coefficient, I guess. There are 2 constants, A and B. B depends on the quality factor. A depends on B. And then you put them into this equation to get your dynamic factor. And ours ended up at 1.3. But we already did that. That would be the same as it was before. KS, that's the size factor that we just set to 1 last time. There is a little bit of guidance in the book on if you want to calculate this, kind of to account for some fatigue type of setup, where a larger gear has more opportunity in the material to have defects. KM, we already have that one. That's the one where you have all of the CM, CMA, all those kind of things built into it. We did that one last time also, and ended up with 1.16. What this is the load distribution factor. So remember, a piece of it was the gear, or the pinion, whichever, mounted on a shaft between 2 supports. And the closer to the center of that span between the 2 supports, the the less slope you're going to have on the gear teeth. So let me kind of describe that over here with some paper. Here's again. So one bearing, another bearing. Let's do one with the gear right in the middle here. All right, so pretty close to the middle. See if we can get it straight. When this thing deflects, you remember there is a radial force wanting to deflect the gear. But when it deflects, and I'm exaggerating the amount it's deflecting here, in this area, I don't have a slope. You know, if I've got it right in the center of a simply supported shaft here, then the slope is 0. But if I had the gear offset, so let's say it's over here, not in the center, when it deflects, when the shaft deflects, now, you know, it's tilted. And so there's this effect of it not being in line anymore. It's got this slope to it. And now this is greatly exaggerated from what would really happen, but there's this tilt to the gear, and this load distribution factor tries to account for that, based on, at least a piece of it is based on how far offset it is. And then there are a lot of other factors in there. How big is it and all that kind of stuff that go into all those little C coefficients that calculate Km. So that's the load distribution factor. So we put ours pretty close to the center, if I remember right, because we don't have a very large Km here. Let's see. dP, that's the, oh, I think it's capital P. Diameter of the pinion, we set that, oh, I must not have set that. Let's see. Oh, for some reason I used a lowercase p on these. We'll, instead of going back and changing all of it, we will change this one to a lowercase p. I think it's technically supposed to be a uppercase p. Let's put it in inches. 2 inches. Let's see what else is in here. The face width, we set this at 1/2 inch. CF, this is a new one. I think we don't have a CF value. Well, it is a new one, but this one is the surface condition, and let's look at it in your book, because it's one that we're just going to set to 1. Got to find the page that it's on in your book first. While we're over here in your book, I'm also going to show you 2 other pages when I run across them, because they're really handy pages. Just got to find them. There's the CF. Well, where are they at? There they are. These 2 pages were zoomed in really close. These 2 pages, page 758 and 759, they basically walk you through the AGMA bending and the AGMA contact, or they call it gear wear. And they go through, show you where all of the different factors can be found. So pretty handy pages on page 758 and 759. So CF is over here on the surface condition factor, or ZR if you're in the SI units. And they, at the time of this book, which, you know, it is the 10th edition is a little bit old, but they have not been yet established. So this is in the place that either AGMA themselves will establish values for CF, or if you routinely use this same set of gears and you've come up with some in-house kind of numbers that simulate this surface condition factor. So, you know, the surface finish on how the gears are made, a lot of times is what this is talking about. There could be an effect. We're going to just use one. We don't have any in-house data. AGMA, at least as when this book was printed, had no data, or at least nothing that was published. So we're going to put a CF of 1, but you might have a reason at some point to put some other number in there. Did I use a capital F? No, lowercase f. Well, we need to tell it it's 1, not ask it what it is. And then the only other value in here is I. This one, so it's sort of similar to the geometry factor J that we had. J we looked in a chart and calculated. I is gonna, that sounds weird to say I is, but let's go get it out of the book over here. might actually have it faster. Well, there it is. This equations here. Right here. Zoom in. 1423. It's two separate equations depending on if you have external or internal gears. So we'll go back to this guy. Internal gear teeth would be like on the ring where they're facing inward. So these teeth over here would be internal teeth. And then all the other gears that you've ever seen before are external teeth, where the teeth, they point out. So these are external, those are internal. And that's the distinction on which one of these you're going to use. So you've got your pressure angle in here. You've got some gear ratios in here. And this MN, it's not a gear ratio, but they tell you down here for spur gears, which is what we're using, you use 1. Otherwise, for MN 1421, which is a few pages over here, you could calculate a different number. But as long as you have a spur gear, you just use 1, which is what we have. So let's put this equation in for the geometry factor. And we're going to use the external gear equation because that is the one where the teeth point outwards. All right, so this will give us I. We already have I written. I equals cosine time. Oh, not really the way I wanted it to write. There we go. Times, let's see, sine for our pressure angle. I did define our pressure angle already. Ours was 20 degrees. Remember, there are 3 common ones: 20 degrees, 25 degrees, and 14.5 degrees. MN, I'll go ahead and put MN in here, and then we'll have to define MN equals 1. Here, MG is the gear ratio, so I don't think I've defined that yet. We'll check and see. But it's just the number of teeth on the gear compared to the number of teeth on the pinion, or the diameters, whichever you have. I think we have both. Okay, I think that's it. Now, like I said, it doesn't know MN. That one is 1 for spur gears. We didn't put MG in. Is we had NG over N, and I believe I used a lowercase p. And already did the let's go ahead and show the pressure angle just so that we have it. 20 degrees. 0.115, so that's our value for I. And then that's all of it, right? All right. Let's go in here, change this to equals, change our WT to one that it can deal with, and see what it equals. Oh, and change this to a lowercase p since that's what I used in the other one. KSI, 81 KSI. So our bending stress was, I don't remember, 30. Oh, no, it was 8 KSI. But our contact stress, 81 KSI. So we have reason to believe that we might be close to the failure point on this contact stress. We do have to compare it to the contact strength from AGMA, not to a number you look out of the chart in your back of your book for some kind of compressive strength or anything. It is a AGMA strength that we need to compare it to. So that brings up a couple of more terms that I'm trying to get over here. So here we have the wear factor safety, or the gear contact endurance strength. We're going to use this factor of safety. So SH equals, and then all of this stuff, which sigma C is going to be the number that we just calculated, the 81 KSI. And then we'll put these others in. Actually, we already have a KT and a KR from previously, the temperature and the reliability. We already have those. We set them to 1. All right, so let's put that equation in. Our factor of safety is equal to, hopefully greater than 1, SC times ZN times CH, all of that divided by KT and KR. Whoa, that really went weird. And then all of that divided by our sigma C, contact stress. Okay, so a lot of these, like we don't have SC right off the bat, so let's work on that one. This is from one of the graphs. In fact, I'll probably have it in here. Let's see. Here we go. So it's one of these, depending on the hardness of the material of the pinion, we can get different values for SC, the allowable contact stress number. We said last time that the pinion was a grade 1. I believe we set hardness at 250 because it was just one of the numbers on the chart here. So I believe that's what we had. We'll check in a second, but we need to take this equation. Again, you could just read it off of here. It's going to be around 115 or so. But we have an equation that we can actually just plug it in. All right, so SC is the equation for it was 322 times, I believe I used HB for the hardness. We do have to multiply by PSI so that the units work out, plus 29,100 PSI. So that's just putting this equation in right here. And 109.6, that seems reasonable. 110, we're looking at this, that seems like it could be 110. I think I said 115, but 110 is even better. All right, so we have that one. Zn is based on the cycles, the number of cycles. Remember, AGMA kind of bases all of these things on 10 to the 7th cycles, but we said 10 to the 8th cycles were the amount of cycles that we intended this thing to operate. So there's a chart also, probably can find it over here. Let's see, this is it, stress cycle factor, Zn. So 10 to the 8th is over here. So we could try reading off the graph, you know, it's going to be somewhere 0.87 or something like that. But there are two equations. Now, the upper line equation is this one. The lower line equation is over here. So we do have to, you know, find where the equation is. But we're going to use the lower one because we're trying to calculate factor of safety. We want to be conservative. And this Zn factor goes in the numerator of the factor of safety equation. So I want the lower estimate here to have a more conservative factor of safety. But there is this range. Now, it's not a very wide range, but there is a range here that it could be in. So if you had a reason to use the less conservative, or maybe take the average, be right in the middle, something like that, you could. We're just going to take the lower one because it's going to be the most conservative. So we're going to use the 2.466 number of cycles. I think I called it cycles to the negative 0.056. So Zn, I guess I erased it, equals 2.466 times cycles. They used the variable n raised to the negative 0.056. And there's the 879, which, you know, that seems reasonable that that's what we would get. All right. CH is, let's see, there is a line somewhere in your book that says for the pinion you use CH. I don't know if I can find it really quickly or not. Hardness ratio factor, CN or CH. When you're working with the pinion, here it is, for the pinion CH equals 1. So typically the pinion is the harder of the two if they have different hardnesses, the pinion and the gear. And so if you're working with the pinion, which we are, you put CH equal 1. If you're working with the gear, then you have to go figure out the ratio of the hardness of the pinion to the gear and put a different number in there from one of these equations. So we just use 1. Let's see, KT and KR, we already have, I think it's a capital T though, isn't it? I don't think it's a lowercase t. We'll just put them out here, but they're just, KT was 1. That's the temperature. If there was some extreme temperature that we were dealing with, then you could have a different number here. We don't have that. Reliability, we're at the 99% reliability, which gives you a 1 value, but you could put, you want more or less reliable. You can put different numbers in here. That's everything. All right, let's move this guy down here and let it calculate. So it is a greater than 1.2, but it is much less. Our factor of safety against bending was 3.627. Against this contact stress, 1.2. Now you do have to be careful with this, and they even make a note of it in your book when they, on those 758 and 59 page, they even make a note down here. Remember, and they make this on the bending stress too. I don't think I said it, but remember to compare SF, so the factor of safety for bending, with SH, the factor of safety for contact. But instead of using SH when you compare the two to see which one is the biggest threat to failure, bending or contact stress, you actually use SH squared when you're comparing the two of them. Because it's based on a stress that changes, the more force you apply to the gears, like the tangential force, the larger the contact area would become. They're smashing into each other harder, so their contact area is larger. So it's a non-linear effect. The more force you apply, the higher the stress, but the larger the contact area. So there's this non-linear relationship between those factors of safety. So if you're going to compare the two to see which one is the worst, in ours, SH being at 1.2 and SF being at 3.6, we're pretty sure that the contact stress is going to be the determining factor of any kind of failure. And then there's another little note in here for crowned gears. So when they have that little bit of curve to the surface, instead of using SH squared, you use SH cubed. And last time we also, I couldn't find the overload factors, the values for them for the different levels of shock. We just used 1 anyway, but here is the table. It's built into these charts for some reason. It's not in the text anywhere. So that would have been better if they put K0, this chart, somewhere in the rest of the text where they talk about K0 or K0. I keep calling it K0, but it's not a 0, it's KO. But here it is in these two charts here. So let's do square this just so we can compare them. It's not going to make that much difference, but let's do it to do it correctly. So let's go ahead and put SF out here. Oh, did I use a capital F? 3.6, and we're going to compare with SH, but SH squared. We don't have crowned gears. 1.4. So it's still, both of them are safe. They're both above 1 for 99% reliability, 10 to the 8 cycles, and this load that we're trying to deliver at this 100 RPM on the pinion. I don't remember the torque that we're delivering. The gear has 125 foot-pounds on it, and the pinion was spinning at 100 RPM. So that power scenario. And it does look like the contact stress would be the most likely to fail. It is not much above 1, but we did take the most conservative approach on, like, the ZN. We took the most conservative approach. Anytime we had a choice to make on conservative approaches, we took the most conservative one. So we should be okay for this scenario. So that is how you would do AGMA contact stress. If you watch the previous video, that's AGMA bearing or bending stress. This is more of a bearing stress. This is contact. The first one, the one that we got the SF number from, that's the bending. And again, we're talking about these two types of failure: bending over here and some contact pitting over here, wear. They call it wear in your book. Clearly that is worn. And this is more of the current way you go about doing gear analysis versus the Lewis equation. The Lewis equation doesn't even tell you about the pitting. It only models this bending stress failure. Okay, that was a shorter one today, but that does get us through the gear equations that we need to do. There are additional things, right? Because what we have looked at is spur gears with straight teeth. You know, they're not helical. And you can have helical gears where the teeth are at a line. You can have bevel gears where they mate together like this, you know, at an angle, maybe not in a 45-degree angle all the time, but at an angle, which changes the shape of the teeth also. They're beveled. So there are other types of gears. You can find all sorts of oddball gear trains too that don't even look round. You know, they're square or whatever. Generally, there's not a reason for that other than it's aesthetic. Most of the time, you're going to be dealing with straight cut spur gears, but there are other helical reasons. There's herringbone that's kind of useful. So herringbone, instead of the gear tooth being straight across here, it's like in a little V shape. So what that does is it keeps the gear from wandering left or right due to some kind of axial force on it. There are times when, so the straight gears, like this one, where the gear teeth gets kind of come across here, maybe you need a little bit more surface area to reduce some pitting stress or bending stress. So instead of having them this way in the same, you know, same width for the gear, you can angle them, right? And so now I get a little bit more surface area over here, but my gear teeth are angled, which induces a thrust load. To counteract that thrust load, you might have a collar back here or a shoulder or something so it just can't move. Another thing you can do if that's not available is you can do herringbone gears, which does this shape. So you even end up with a little bit more surface area, and now I have opposing thrust forces on this from the two different angles here. So this is herringbone, this is helical, this is just a straight cut, and each one has a reason why you might use one or the other. So here you're increasing the surface area, increasing the size of the gear tooth without increasing the width of the gear blank. Here you're doing the same thing, but you're also counteracting any thrust load that might be generated by having opposing thrust loads. So you do end up with some more friction type, power losses in these gear shapes, but you end up with other benefits. So, those might be useful. And then you have the bevel gears that I didn't draw a picture of, but the ones where they're kind of chopped off at an angle here so they can mate at a non-planar angle. They're in two different planes. So there are other things. Your book does cover some of those if you ever need to run into them. In fact, this book, or one like it, is pretty good to keep around because it does have such a wide variety. You've got in the front half of it, you've got all of your failure theories, and the second half of it, you have all those failure theories applied to specific applications, springs and gears and shafts and all that kind of stuff. We do have one more topic Friday, and that will be an overview of some of the friction elements, so brakes and clutches type things. There are a couple of chapters in here that we didn't get to cover specifically. It's kind of like, I don't know that we'll get to V-belts, although they do kind of work like the friction elements in a way. They're based on friction to operate. But there is a little bit of a chapter on that. It's not a complicated thing, so I'm not too worried about not covering that specifically, but that is also in the book. I think we're good for today. We'll be back on Friday with the friction elements, and that'll be the last topic. And then there's an exam on Monday, and that'll be the last exam. Also, you can do your evaluations. Don't forget to do those. They're online. You can go fill those things out. And I did open up the quiz, the very first quiz you took on like the first day. I put it at the last day, and you can retake that thing. And it's the one that has all the overview of just nomenclature type stuff. Hopefully you are able to do much better this time now that we've gone through a lot of these different pieces. And I opened that up. You have the evaluations. We have test on Monday. And I think there's a couple of homework assignments to finish off. All right. I will see you guys on Friday.